Alright, we are finally moving on to resonance after talking a whole bunch about alkenes. And you may be wondering, why am I introducing resonance in the same unit as alkenes? And that's because, well, also, why are there unicorns, dragons, and rhinoceroses? That's because alkenes, due to their p orbitals, can have their pi electrons delocalized potentially across the whole molecule, depending on whether there's a whole bunch of p orbitals lined up. Before I move on, I just want to give credit. This is probably the best representation I've ever seen for resonance, where you have two resonance contributors and the combination of those two. And I'll give you a hint. Well, first of all, this is from Bruce, Organic Chemistry textbook. I'll give you a hint. Which ones are real and which ones are not real. That's the beauty of this picture. And all will be revealed maybe at the end of this video, but definitely by the end of the second video on resonance. But let's get started. Whoa. Is that focused? We are going to talk about resonance for the first time. And in a previous video, when we were talking about our first reaction with alkenes, which is hydrohalogenation, we went through a carbocation intermediate. The carbocation intermediate was this. Okay. And what did we learn about carbocations? We learned the trend, tertiary. Carbocations are greater than secondary, greater than primary. Greater in what? Greater stability. So I definitely need to write that. Tertiary carbocations. But why is that the case? Why does it add stability? It's the idea that if you could spread out the charge or reduce the charge by spreading it out or sharing electrons, that will stabilize the molecule. So this was stabilized via hyperconjugation. This is review. This was, what video was this? This was video 03F20. Is it really true that we're mitigating that plus charge? Well, if we draw out one group to the right, one methyl group, okay, there's an alkyl group, and let's just go ahead and put, well, let's make this carbocation secondary. So this carbon only has 3 bonds, and we have a plus charge here. In the p orbital, it's empty, so it can accept electrons. And we mentioned that hyperconjugation is the sharing. You're not really transferring electrons. You're not making a new bond. It's just sharing some electron density because of some overlap between the sigma and the p orbital. By sharing electron density with this empty p orbital, do you realize that we lower the plus charge? We make it less positive. So now positive is less positive. It's not a full positive charge. So another way we could say that hyperconjugation is stabilizing the carbocation, we could in general say delocalization of the charge. We're actually making this bond more partial positive than it would be because it's giving up electron density. But ultimately we are delocalizing charge. We're not having it static on just this carbon. We're kind of sharing that plus charge with the neighboring carbons. And delocalizing charge is stabilizing. Well, great. We talked about this carbocation because it's an intermediate. It's an intermediate when you react a hydrogen halide plus the alkene. Okay, and it will go on to put the chlorine here. Okay, great. What are we talking about resonance? I don't see any resonance. Remember what resonance was in general chemistry? Resonance was, you can think of it as a shifting of
bonds to create different Lewis structures. So for instance, we might have talked about this. Did we talk about this yet? Let's take a nitrate ion. Okay, go back to general chemistry. And we'll come back to stabilization in just a bit. But nitrate looks like this. Okay. We have something missing. Before you move on, always double check formal charge. It's interesting because NO3 you learned as NO3 minus, but it's minus because when you look at the charges, we have 2 negatives and 1 plus. We don't have just 1 negative to make it minus. We have minus, minus, plus. Resonance, I'm not sure if your general chemistry professor showed this, but when they asked the class to draw NO3, well, maybe some of your classmates drew this. Now, you may wonder, well, aren't these two structures the same thing? Right. It seems all we did was we rotated this molecule clockwise to get the double bond oxygen up here. Yeah, it looks like that. But when you have resonance and you draw this resonance arrow like this, the double-headed arrow indicating resonance, what you're really saying is that keep the atom static, and this oxygen atom has partial single bond character, partial double bond character. So if there's a way for us to mark the atom like star, it's not that the star now is down here. This is still the starred oxygen. It's just that now it has double bond character. In organic chemistry, not only do we need to know how to draw the resonance structures, but how do we go from one structure to the next? So we do have to use mechanism arrows, but this is not a mechanism for a reaction. It's a mechanism just to show different Lewis structures, different resonance structures. So we could count this as resonance contributor number 1, and we have another resonance contributor number 2. There's actually a third one, and I will challenge you to, on your own, draw the mechanism arrows to get to the third resonance structure of nitrate. Okay. Now, think about what we just did. See, this oxygen has a negative charge, but in this resonance structure, it doesn't have a negative charge. We actually delocalized it into this oxygen right here. Right? This became charged now. We are spreading out the charge. By spreading out the charge, you're making this ion more stable than what you would normally think its stability is. Resonance, we have this phrase. Let's add another one. Resonance is a stabilizing effect. E-F-F-E-C. Gotta slow down a little bit. Resonance is a stabilizing effect. Alright? I know people tend to forget their chemistry once the semester's over. If you need to, I think it'd be worth looking at your general chemistry notes when you did resonance. And now, as an organic chemist, okay, you can now draw the mechanism arrows to literally show how the electrons move. Let me give you one other rule. Another phrase, another pink quoted phrase. In resonance, or you can say with resonance, atoms don't move, only electrons. I am purposefully making my mind think these atoms are static, and I'm keeping track of the oxygen that's starred, and in some instances it's single bond, in some other instances it's double bond. In this resonance structure it would be single bond. Okay, we go back to negative because we're actually just moving these pi bonds, so each oxygen at some point has a double bond. Okay, but remember this,
because maybe they'll show you an example. They'll show you two structures and they ask you, is this resonance? Well, if an atom moved, then it's not resonance. If you notice that it was a different connectivity, it's not resonance. Okay. Man, how do I connect this to alkenes? Well, take a look at this molecule here. It's a carbocation, and it's actually primary. But it has a special name. It's called primary because it's on a primary carbon, but because it's next to a double bond, it has interesting properties, interesting stabilization properties. This is called primary allylic. When your carbon of interest is off of a carbon-carbon double bond, you can say that this carbocation is allylic. Now, primary carbocations are typically considered not very stable. Okay, they're the least stable out of these three. But when you have it allylic, what could we do? We could draw a a mechanism arrow to show a resonance structure. Okay, so understand my terminology. We're drawing a resonance arrows to give us another. Did I say that right? We're drawing mechanism arrows to give ourselves another resonance structure. We are drawing resonance. Slow down. We are drawing mechanism arrows to give us another resonance structure. Don't say anything. I know it's a mistake. Trust your pink arrows. Your pink arrows are telling you that the pi bond now is shifted to the left. We have this bond to a carbon on the right, and this carbon has two hydrogens. This carbon still has two hydrogens. So be very careful, because when you draw that, I know you're trained to make every carbon tetravalent, to pretend that there's enough hydrogens to make that carbon have 4 bonds. But you got to remember, atoms don't move. So if there were 2 hydrogens here, in resonance, there better still be 2 hydrogens here. That's tricky, because again, you are trained to automatically think that when you see a structure like this, there are 3 hydrogens there. Okay, but they're not when we draw this resonance because atoms don't move. Did we make this carbon at the end neutral? Yeah, because how many hydrogens are here? There are still 2 hydrogens here because it's a carbocation, and then we made the double bond to give it the 4th bond. That's why resonance is here in the same unit as the introduction to alkenes, because carbocations, anions, also next to a double bond that are allylic, those are resonance stabilized. Okay, that's one example. Now, at this point, man, you may still be studying how to use mechanism arrows to make different reactions. Now I want us to use mechanism arrows to show different resonance structures. It's going to take some practice. Let me just show you, before I move on to another example, why do we have this resonance? Okay, it's really interesting, because if you think about the hybridization, you know that this carbon is sp2. You know that this carbon is sp2. And hopefully you know that carbocations are flat and sp2. Okay. The way we did this in previous videos is that we counted the number of balloons. Knowing that there are 2 hydrogens here, this carbon has 3 balloons, sp2, and s plus a p plus a p. There are 3 atomic orbitals that make up the hybrid orbital. What do we know about sp2 atoms? sp2 atoms have p orbitals.
unhybridized p orbitals. Where's our double bond? Our double bond is here. Okay, so we have a sigma bond. I'm not drawing the sp2 orbitals. And we have a pi bond. But because we have a p orbital next door and it's empty, there's overlap between these p orbitals. So therefore, this molecule can share these 2 electrons over 3 carbons. And again, you have this. Okay. Resonance arrow. And that. And these are your 2 carbocations. Okay. If you're thinking again that all we're doing is flipping this molecule, no, we're not flipping this molecule when we have resonance. We are literally keeping the atom static and just moving the electrons. And I could prove that to you, or I could at least demonstrate that to you. Because what if I have this molecule? Oh, I better do this correctly. Did I mess up already? That molecule. Okay. Well, if I draw the mechanism arrow, be very careful. That arrow has to be pointing to the bond, not to the carb. Okay. I think that's close enough to the bond. Okay. Just want to make sure your grader doesn't get confused. All right. Based on my mechanism arrow, can you draw me the resonance structure, the other resonance contributor? Pause the video and draw me the result of this arrow. Okay, the result of this arrow is that we shifted the pi bond to the last 2 carbons, and then this carbon is naked. This carbon lost a bond. See, this carbon didn't lose a bond, right? This has 4 bonds because of the hydrogen. It still has 4 bonds. It's this carbon that's naked. Now do you see? These are really different. So it's not that I'm rotating this or flipping this. It's literally I'm moving electrons to give both of these carbons equal sharing of the plus charge. Equal sharing of the plus charge. And over here, how did I show that it's not just rotating the molecule or flipping it? Because literally we have a secondary carbocation and here we have a primary. But they're both allylic. Let me just cover this up. Allylic. One's primary and one's secondary. So yes, one is more stable, secondary allylic, because this is primary. But the thing about resonance is this. Think about the 2 molecules that we drew, the 2 allylic carbocations. Which pictures represent those 2 molecules? This one, resonance contributor, resonance contributor. What do you know about these 2 creatures? I'm pretty sure they're made up. These don't exist in the real world. These don't exist in the real world. Even though we could draw the line structure, these actually aren't isolatable, which is kind of strange to think about it, because when we do reactions much later with allylic carbocations, we are going to get products. They do exist, but not in this form. They exist as a hybrid. How do I draw the hybrid in this case? And it's a resonance hybrid, that's what? The resonance hybrid is real. That's one skinny rhinoceros though. So the resonance hybrid is real. Let me just mark that up real quickly. I'm trying to pick a color. This is a unicorn. What was this? The dragon. And I backed myself into a corner. Rhinoceros. Oh, there's an H. Rhinoceros. Okay, it's the one that's real. Rhinoceros. Not close at all. Okay, how do we draw the hybrid structure? Okay, you ask yourself, the first carbon-carbon bond is always single. Okay. The second, the 2 to 3, it's double and it's single. The average is 1.5. 1.5. The last 2 carbons, single, double, 1.5. 1.5. The plus charge is a little bit strange. Either you could put plus charge right here in the middle. You'll see that a lot of times. So the resonance hybrid does have a full plus charge. It's just that that plus charge is shared between 2 different carbons to total up 1 plus charge. Or I think it's acceptable to draw a partial positive here, partial positive there. This is real. The thing is, as chemists, chemists don't really want to keep drawing dotted lines because there are a lot of molecules that participate in resonance. Most of their molecules in DNA participate in resonance. Heck, all your peptides, it's called an amide bond. Amide bonds participate in resonance. So to have to draw all the hybrids with the proper dotted lines, it's a pain. Not only that, it's a pain to kind of figure out where the plus charges are. I mean, you can by looking at the line structures of the 2 resonance structures, but if I'm just drawing an allylic carbocation, I have to figure out, well, where are those plus charges? It's much easier to draw one of the resonance contributors, just like this, right? When you're asked to draw a nitrate, you could draw this one, or this one. But to tell you the truth, none of those actually exist. All of them have 1 1/3 bond. 1 1/3 bond. And if you recall GenChem, that's when you did bond order. 1.33. Okay. Don't worry about that. We're not doing bond order in organic, but we do need to know that, again, these don't really exist. It's a hybrid that exists. But even though that these don't exist, these are acceptable structures. Acceptable line structures, or if we drew out all the letters, acceptable Lewis structures. Let me give you, Let me give you some rules. I have time. And these rules are how to move electrons in resonance. Because you just can't take any electrons and put them anywhere you want to make a new valid structure. Okay, I'll use the word valid. Okay, because there's going to be invalid structures that you should not count as resonance structures, but that's in a different video. But I want to first figure out what about these movement? Like, what are the rules? Because why couldn't I move these, 2 electrons all the way to the carbon and make a carbon with a lone pair? So let me give you those rules. First, we'll use bullet points. You can move the 2 blank electrons of a double bond to an adjacent blank or to an to an adjacent blank. Okay. You can move 2 pi electrons of a double bond to an adjacent bond, or to, sorry about that, an adjacent atom. Ah, that's strange. But we did it here. See that pi bond? We moved it to the adjacent bond. Moved to the adjacent bond. Okay. Second bullet point. You can move 2 electrons. Of a lone pair only to an adjacent bond. We haven't seen that. We might have some time to show an example of an anion. See, these are carbocations. Maybe we could do a carbanion and show how it can do resonance as well. But lastly, nope, I think we're good. Those are the only 2 rules. The other thing I had down here was, warning. Not a rule, but warning. And it's a very important warning. Don't make 5 bonded carbons. Let's take a look at one of our carbocations. Okay. Let's use our rule. A pi bond to an adjacent bond or to an adjacent atom. So this is good, right? This is what we actually did above in this paper. And I'm going to call this valid. Valid. But if you're not very aware of how many hydrogens the molecule has, then you may think that, well, why don't I move it to the left? And maybe I have this. Okay. True, I didn't move the plus charge, but there's something even more devastatingly wrong with this movement of electrons. What's really, really wrong is, see this carbon here? It has 3 hydrogens. Well, if I move these 2 electrons away, well, heck, that carbon is positive, right? Because we lost the bond for that one. But also, oh my goodness, the 3 hydrogens. 1, 2, 3. So bad. And we could say this is not valid. Not valid. There are many things why this is not valid. Like, you don't want to have 2 plus charges next to each other, but you definitely don't want to have a carbon with 5 bonds. Okay? So even though we follow this rule, you got to be aware of your hydrogens. So a lot of times the practice is, I know we love the line structures because they're so easy to draw, but maybe we should draw the hydrogens as well to realize that, you know, there's 1 hydrogen here. So when we remove that double bond, we have a plus charge there, right? That one's fine. 2 hydrogens, 2 hydrogens. But this one is ridiculous. 3 hydrogens. Okay. This rule here, you can move 2 electrons to an adjacent bond. Let me give you one example, and it's going to be tight. Well, oops. Let me show you this example, and then we'll be done, at least for this first part of resonance. You could move a lone pair to an adjacent bond. So when I do this, you notice that this carbon now has 5 bonds. A double bond, and a single bond. But we can resolve that by moving that. So this is an example of resonance with an anion. And we're going to do more examples in the next video with anions, a few more cations, and also some neutral molecules. But I just wanted to show you this example only because of, well, mainly because of this rule right here. You can move 2 electrons of a lone pair to an adjacent bond only. And we have that there. Okay, that's the lone pair we're moving. Here we're moving a pi bond. Oh, what rule did we use there? You can move a pi bond to an adjacent atom. So actually we've seen all 3 cases. Pi bond to a bond, sorry, pi electrons to a bond, pi electrons to an atom, and lone pair to a bond. Okay. That was a lot. Hopefully you'll have practice problems. We're going to continue our discussion of resonance in the next video.